So without waiting more, I would like to introduce the first plenary speaker this morning. So Professor Martha Grover is with the School of Chemical and Biomolecular Engineering at Georgia Tech in the United States. She obtained her bachelor in 2002 from the University of Illinois Urbana-Champaign in mechanical engineering. Then she moved to California, where she got an MSc and a PhD from Caltech, also in mechanical engineering. She joined Georgia Tech in 2002 as assistant professor. She got an NSF Career Award in 2004. In 2011, she was awarded the Young Outstanding Researcher Award from the CAS division of IECHE. What I can tell you about the research activities of Maria is that her research is dedicated to understanding, modeling, and engineering the self-assembly of atoms and molecules to create large-scale structures and complex functionality. Her approach draws on process systems engineering, combining modeling and experiments in applications dominated by kinetics, including surface deposition, crystal growth, polymer reaction engineering, and colloidal assembly. Her plenary address this morning is entitled Control of Self-Assembly with Dynamic Programming. So please join me to give a warm welcome to Martha. Martha, over to you.
So it's great to be here and to kick off the conference and tell you about the work of my research group in control and self-assembly. As was just mentioned in the introduction, I'm from Georgia Tech, the Georgia Institute of Technology. It's located in Atlanta, Georgia. So that's shown with the arrow there. We're in the southwest corner of Georgia, so really not near the ocean. We're by in the foothills of the Appalachian Mountains. And Georgia Tech is located right in the middle of the city of Atlanta. So Atlanta is a city of about 500,000 people, about 6 million in the metro area, and is the home of Coca-Cola and CNN and the birthplace and hometown of Martin Luther King Jr. So that's where I'm coming from. So first, I want to really just set the stage and talk about some of the principles of self-assembly. What I mean by self-assembly, define a little bit of terminology. Basically, by self-assembly, I'm talking about a many-body dynamic system, a collection of particles, and many of those particles will be indistinguishable, although certainly we could have more than one type of particle. As a result, there are many symmetries in this many-body dynamic system that will allow us to do state reduction of this high-dimensional system. Today, I'm going to be talking really about non-covalent interactions between these particles, but more broadly, in my group, we also look at covalent interactions, and mathematically, and we can treat these similarly. So really, it's a broad set of interactions. And by self-assembly, the term really means that the particles are interacting with each other and assembling on their own, so that's kind of counter to feedback control. But we can manipulate the interactions with fields. So by control of self-assembly, I mean that we will have a process input, and we will manipulate the fields, which are usually low-dimensional in terms of the input space, and then we will act on all of the interactions between the particles, but perhaps not all equally. We also need to specify a desired state, and if we do have this manipulated variable, that gives us the option to either drive the system into a metastable kinetic trap or to drive the system to the low energy crystalline state, and really I'm going to be talking today about that latter case. So within my group, we look at this general class of problems and also look at very specific applications. And some of these are illustrated here. This is nanoparticle deposition, silver nanoparticles on a paper surface for antimicrobial properties. In the middle image, this is actually an experimental atomic force microscopy image with image processing used to quantitate this image data. This is a polymer organic electronics application where we get a fibril morphology of our conjugated polymers. And finally, in the lower image is representing pharmaceutical crystallization. And if we think about the broad class of kind of materials design, First, we can think about a step where we design the chemistry, or we make decisions about what molecules to use. Then that choice of chemistry influences the process, how we process the material, and that gives us a resulting structure. The structure of that material then determines the properties of the material. So these are all very important steps in producing a material, but in my group, and especially today, we'll focus on the process-structure relationship, which is really central, I think, to process systems engineering. In my research group, we look at problems in materials processing and separations, and also in how self-assembly is important in achieving biological function. And most of this research is within the context of chemical evolution, how the transition on the early Earth may have gone from chemistry to biology at the origins of life, and more broadly, how we can understand the ability of systems of molecules to evolve. This field has recently been coined systems chemistry, which I find interesting as a process systems engineer, but definitely it's a complex system, not a reductionist chemistry problem. So this is one project in my research group where we looked at peptide-based monomers, how they polymerize, and that drives a phase separation into these droplets. Then the peptide assemblies will nucleate, and then they select out the trimer through these fibers that also can show catalytic function. So we're really trying to show here how these properties of self-assembly, polymerization can then feed back to drive selection processes, and how this process may have occurred on the early Earth. But today I'm going to focus on our work in crystallization, which involves explicit model-based feedback. So let me say, again, a few words about crystallization, what that term means to me in this talk. So the crystalline ordered state of a material is very important for many engineering applications. It's important for separation. If we have a molecule dissolved in a solution and we can crystallize it out, that makes it much easier to separate. And I'll talk a little bit about our work in nuclear waste separation later on in the talk. Crystallization is also a very effective method for purification. If we crystallize one material that we want to purify, that crystalline lattice will tend to really exclude other species. So this can give us a very high fidelity purification process. This is very important in the pharmaceutical industry. Finally, crystalline ordered state is also really desired to achieve high material properties, such as electronic properties and optical properties in materials. So achieving a highly ordered state, crystalline state, is very important for many electronic devices. The crystalline state is generally the low energy thermodynamic ground state. Of course, there may be multiple crystalline structures if polymorphs can exist in a system, but typically this crystalline state is of a lower energy than an amorphous state or a defected state of the crystal. So that's helpful in trying to achieve this desired crystalline state, that it is the thermodynamic ground state. However, as we process a material, sometimes defects can form, and those can really become locked in as kinetic traps. And often these defects can really drive the properties of a material. So it's really important to generally to try to avoid such defects forming. So we could wait an infinitely long time in order for the system to reach its thermodynamic ground state, but of course that's not practical for a high throughput manufacturing process. We'd like to process the material rapidly. And this leads to what's sometimes kind of understood as an inherent trade-off between kinetics and thermodynamics in materials processing. So really one of the ideas that I want to put forward here is that feedback can really help circumvent this, what seemed like kind of an inherent trade-off between kinetics and thermodynamics, where we only intervene when needed, when we see a defect starting to form. So the idea of applying control in crystallization is not a new idea. In particular, Jim Rawlings has articulated many of the problems and solution approaches for control of crystallization, including this paper published in 1994. So I just want to summarize here what I think are some of the key approaches, particularly focusing on experimental approaches to control of crystallization. We do have a conference paper that really summarizes much more broadly the field and the literature. So I just want to mention a few of the highlights here, especially as it relates to experimental implementation. So it's been recognized that dynamic process inputs can be helpful in crystallization. This could be something as simple as a linear cooling profile used in batch cooling crystallization, where we start off having a fully solubilized solute, and then we lower the temperature, and that then creates a supersaturation to drive nucleation and growth phenomenon. But there are also other time-varying inputs that can be helpful, such as a periodic switching. Switching magnetic fields have been used in the colloidal assembly of microparticles, and I'll talk more about that application later on in the talk. Temperature can also be switched between levels for shape control, and that's something that Mike Doherty's group has demonstrated. In the case of closed-loop feedback, we can take either a model-free approach or a model-based approach. Some examples of model-free approaches include simply applying PID control, which was demonstrated for colloidal assembly by my collaborator in this work, Michael Bevan, back in 2012. In the case of small molecule crystallization, many approaches have been implemented, including direct nucleation control that is used to trigger a change from heating to cooling based on a backscattering measurement from a focus beam reflectance measurement. In the case of model-based control, of course, we can compute not simply a helpful action, but an optimal action. And the work and platform laid out by Jim Rawlings several decades ago with population balance modeling and model predictive control is one approach that has been studied quite a lot in simulation and very little in experimental implementation, I'd say. So I wanted to particularly mention this paper led by Ali Mesbah with Zoltan Nagy and from Paul Vandenhove's group over 5 years ago that implemented nonlinear model-based control using population balance model in experiment. In this particular case, they focused on controlling the growth rate of the crystal, which is directly related to the supersaturation. So the structural information of the crystal itself was not measured in real time or fed back. But I think it's a notable experimental implementation, I think the only one that I'm aware of. And they also noted the challenges in discretization and solution of the nonlinear optimization online. So in my research group, we've been taking an alternative approach based on dynamic programming. As a result, we're able to do the computation offline. And also, we have not been relying on the population balance framework. We also do population balance modeling, but sometimes the population balance model doesn't fully describe the behavior over the range of inputs we'd like to consider. And so we have been taking alternative approaches, not restricting ourselves to population balance modeling. So I'll talk about that now. And I'm going to do that in the context of these two case studies. First, I'm going to talk about colloidal crystallization. A colloid is simply a collection of solid particles suspended in a liquid. Colloids is the term used in the community to describe those systems. So we're going to look at crystallization of these microparticles, and then also small molecule crystallization in a salt crystallization process. So there are many challenges to applying control, feedback control, to these many body systems. One challenge is that there's a large state dimension. So if we have many bodies, then we have many positional coordinates for each of these particles. So that's one challenge. Another challenge is that the dynamics are inherently stochastic as well as nonlinear. So the molecular motion is random, and that leads to a randomness in these processes. And also due to molecular interactions, the potentials are highly nonlinear. In addition, we typically have limited actuation of the system. So certainly one could consider a case where you take an atomic probe and move individual particles around, but this is really not very scalable in a manufacturing setting. So that's a kind of a top-down approach, but the bottom-up approach of using self-assembly, a limited number of actuators through fields, is much more scalable. to a high throughput manufacturing process. So in that case, we typically have limited actuation, certainly many fewer actuators than the number of particles in our system. But we still have influence. And so the question is, what can we do? Typically, we also have limited ability for sensing in real time. Now, I'm going to talk to you today about the colloidal assembly problem where we have full state feedback. And so then we can really ask, what can we do if we have all that information? But typically in a manufacturing setting, you wouldn't really have all that information. However, there have been a number of sensors and technologies developed in recent years, largely driven by the pharmaceutical industry and the process analytical technologies initiatives that do provide new capabilities for sensing and then real-time control. So I want to introduce this particular application here of the colloidal assembly with these images that really does highlight especially the challenge associated with the large state dimension. So on the left is a collection of particles, about 300, and they're in basically a fluid-like state. Okay? So they're very disordered and not very dense. On the right, we have a crystalline configuration where we have this ordered hexagonal lattice in 2 dimensions. And so that's going to be our desired configuration for the system. And then in the middle is an undesired configuration. This crystal has grain boundaries, and that's very detrimental to performance in general for the material to have these grain boundaries. So that would be an undesired state. And in order to characterize these crystals, colloid scientists use order parameters. Here, C6 and Psi6 are 2 order parameters that are going to be important throughout this talk. C6 is the local ordering. How many particles have 6 nearest neighbors in this hexagonal lattice? Okay. So on the left, C6 is low. It's well below 6. But in the middle, C6 is actually quite high because locally, most particles are in that hexagonal lattice. And finally, in our desired structure, we're much closer to 6, although particles on the edge can't have 6 nearest neighbors, so we're never going to achieve 6. Okay. So Psi6 is a different order parameter, also used by colloid scientists. And this describes the global order of the system. So we have local order and also global order. So in the fluid-like state, we have low global order, whereas in the desired state, we have high global order as desired. But in this undesired state, we have low global order. Okay? So we have high local order, but low global order. We can't map all particles onto a single hexagonal lattice. So these order parameters are going to be important as we go forward. So in my group, over the years, as the years go by, we've really developed this methodology, first in simulation. So it's a publication here in 2008 from my group where we demonstrated this approach in a lattice Monte Carlo simulation of crystal growth. But we've been developing it further in the context of specific applications and in terms of experimental application, and I'm going to talk to you about that today. But here are the 3 steps. So the first step is to select variables that characterize the aggregate state of the system and can be measured in real time. So this is the challenge. These order parameters may be good candidates for the aggregate state of the system, but certainly there's no guarantee that they would be complete. We really need to have a Markovian state in which, based on the values of this aggregate state, we can predict the future state, and in a memoryless context. And then we also need to measure these in real time. So in these 2 case studies, I'll show that we have been able to find a collection of aggregate variables that meet this criteria. I would say this is the most difficult part of this methodology in our experience. The second step is to take this aggregate state and to use machine learning to develop an empirical model of the system dynamics in terms of this state. So once we have a Markovian state defined, now we can build this model using whatever regression technique we like We can call it machine learning, we can call it empirical modeling, but we need to be able to make predictions in terms of this reduced order state. Once we do that, then we can apply dynamic programming or another control methodology based on this predictive low-order model to obtain our optimal state feedback control policies. And in my experience in the applications that we have looked at is that dynamic programming is very convenient. We can compute this offline policy, have a table lookup, and it provides also a nice way to engage with our experimental collaborators to help them understand what this policy is doing. So dynamic programming has worked well for us in these particular applications. So now I'd like to really talk through this application in colloidal crystallization in terms of the details of the hardware and the method, and then the experimental implementation of the optimal feedback policy. So as I mentioned before, a colloidal system is a collection of particles suspended in a liquid, and if these particles are crystallized, they have interesting optical properties. So because they're about a micron in size, they're similar to the wavelength of light, and they interact with light in novel and interesting ways. So it's possible to create circuits based on light, and these circuits would be really lossless compared to having circuits based on electrons. So, but the materials need to have very low defect density. So a grain boundary like this would be very detrimental to an optoelectronics application. There are also other applications, maybe more futuristic, of these metamaterials in which you can bend light around objects, creating invisibility cloak. But this has only been demonstrated at very small length scales because it's very difficult to rapidly manufacture these defect-free materials. So that's kind of the engineering application for these metamaterials. But colloidal crystallization is also of interest in understanding nucleation and growth phenomenon. Because the particles are large enough to see under a microscope, we can really observe their movement. And so these colloidal crystallization processes are used to understand molecular and atomic nucleation growth phenomenon as well. Of course, they're a little bit different than atoms, but they can kind of be treated as atoms. But this provides, I think, a really great opportunity for also understanding our ability to crystallize not only micron-sized particles to control the crystallization, but also to understand our ability to crystallize and control atoms and small molecules, because we have full state feedback. So as I mentioned previously, a challenge in control of crystallization is to avoid these kinetic traps and to use feedback to intervene only when necessary. But we're going to try to drive the system from this fluidized state to this crystalline state and to avoid this defected state. So here's some details about the experiment. These experiments are performed in Michael Bevan's lab at Johns Hopkins. So he's my collaborator on this process. And they have this quadrupole electrode. There's a single scalar AC input to the system. So we just have one manipulated variable. But it's applied across these 4 electrodes. And in the middle are these particles, about 300 particles in the results that I'll be showing you. And the particles are made of silicon dioxide, silica. There are about 300 of them, and they're about 3 microns in diameter. They're suspended in water. So this is the very simplest colloidal system you could think of. Later on, we could talk about different shaped particles and functionalizing them with patches and DNA, and there are all sorts of possibilities. But this is the very simplest case you could think of, and I think that's important to really be able to focus on the feedback phenomenon. Still, it's tricky. We're looking at a quasi two-dimensional assembly, so we're going to restrict our voltage input to below 2 volts so that we don't buckle into a 3-dimensional assembly. Of course, we could also look at 3-dimensional assembly, but it's easier to start with to look at 2-dimensional assembly, and then we can really see where all the particles are more easily. Another key feature of this system is that these interactions between the particles are weak enough such that we can act in the reverse direction and pull them apart again. So this is a very important property if we want to implement feedback, or at least it's very helpful to be able to pull them apart. So we have these KT scale interactions. Also, depending on the frequency of the AC field, we can either push all the particles towards the center of the well, or at a lower frequency, we can actually pull them apart. In the work that I'll show you, we've only pushed them together or relaxed the pushing so that we keep all the particles in the field of view of the microscope. But there's more capability for aggressive sensing in the future by switching the field. So it's kind of interesting phenomenon. And finally, our feedback is going to come from real-time monitoring under a microscope. We take video and watch the particles assemble, do image processing on the fly, calculate center of mass of particles, and then use that for our feedback control. So here's the block diagram. We have our process, we view it under the microscope, we feed that back to our controller together with our desired structure, in this case in terms of the order parameters, and then we command the voltage for the next time step and go around the loop. So I'd like to show a movie now. This is an experimental movie, and you can go ahead and get it started in the back. So we start in the fluidized state, and then the voltage, represented by this lambda here, goes high, but we have a grain boundary, but it's slowly working its way out, actually, but it's very slow, but there it goes. So it works its way out. So, okay, let's try again. This is an inherently stochastic system, so every realization is going to be different. Let's push hard. We have a void in the middle there, but no grain boundaries. So try again. Now we have a little grain boundary, but that one worked itself out quickly. So I think the potential for feedback is very high in manipulating materials at the molecular and nanoscales because it's inherently stochastic. So that's really a case when we very much need feedback. Here we have a terrible grain boundary down the middle, so that's just never going to go anywhere. Eventually it would work its way out, but it might take an infinite amount of time. So this is a case where if we want to get rid of this, we probably need to intervene and take some kind of action. Okay, so we can go ahead and move on to the next slide. Let's see, maybe I can do that. There we go. Okay. So this system is actually pretty well understood in terms of the physics. So we have a really good first principles model. Not perfect, but really quite good. That was developed by my collaborator, Michael Bevan, and the reference here is published in 2009. We can really understand the forces on these particles. The assembly is driven by particle field interaction with the AC electric field, with dielectrophoresis, so there's an induced dipole because of the inhomogeneous electric field, and so that drives the particles towards the middle or away from the middle. But we also have particle-particle interactions. That's more of the self-assembly kind of phenomenon, where the particles interact with each other through repelling through electrostatics and also through dipole-dipole interactions between the particles. And then the particles are also stochastic. So these colloidal particles are small enough that they still have significant Brownian motion, and that contributes strongly to the stochastic behavior of the system. So that also can be included in a simulation that's referred to as a Brownian dynamic simulation because we have this random Brownian motion. And the equations of motion for each particle, F equals ma, can be integrated forward in time to make predictions about the system evolution and how that will depend on our process input, the voltage. So these model parameters for this particular system of colloidal particles, silica particles, with this electrogeometry really has been characterized well by the Bevan group over the years. And so from basically first principles, we can make predictions about the system that are quite accurate. Okay, but this is a very high dimensional simulation. We have 300 particles, then we have 600 coordinates in 2 dimensions for the Brownian dynamics. So then, as I alluded to earlier, the real challenge is to figure out, is there a reduced order state representation that mostly captures the behavior of the system, and that because our particles here are indistinguishable, we're not trying to place particle 1 in one location, particle 2 in another location. We're trying to achieve these overall crystallinity. There certainly are symmetries, so we should be able to reduce the state dimension. But then the question is, well, how far can we reduce it? So we really try to move from this describing the system in terms of particle coordinates and location, which kind of represented on the left, to the order parameter representation, or a reduced order configurational representation. So if we look at the position of an individual particle in this electric field, we can see that the potential energy of the system is really minimum at the middle for our 1 megahertz voltage. If we switch to 0.1 megahertz, then it becomes repulsive. And so we can view the forces on the particles in terms of this energy representation in Cartesian coordinates. But we can also then, based on kind of domain expertise and also potentially automated state reduction, move to describe the system in terms of order parameter. So this is a figure representing the attractive frequency in terms of our order parameter C6, which is our local crystallinity coordinate. And we can describe the overall free energy of the system in terms of the average value of C6, our local order. We also might want to include global order. We can certainly consider higher dimensional representations, but how that would change as we change our voltage input. Okay? So this is a way that we can understand kind of our ability to drive the assembly. And this is a framework that really has been developed in the colloids community. So this is not something that came out of our control research, but this is how colloid scientists think about characterizing the system and making predictions about its evolution in terms of free energy as a function of order parameters. So real question is, can we also use this representation for control? Really, is it going to be a Markovian state representation? Okay, so around 2012, I started collaborating with the Bevan group in this area, but this study here is really kind of the launching off point. So they had already been implementing a model-free control with a proportional control law. And they wanted to really track these set point changes in the order parameter, in the local crystallinity. And they used a proportional controller to do that. But then it didn't really work that well, so they thought about what's going on, and they came up with this kind of hybrid control law where they would switch between the attractive frequency and the repulsive frequency. So there's a little bit of logic here, depending on the value of C6 and how, really, what is the error in the system, right? So here's the error in the system, C6 desired minus C6 measured. And, but they have a proportional control law here. And so what they found was that it kind of worked, that they could kind of, there's a lot of stochastic phenomenon here because the system is very stochastic, but they could really drive up the crystallinity, condense the system, achieve a much more ordered structure, although it still had some defects and they weren't fully able to track with their proportional control law. So this is when I started talking with the Bevan group, and they really wanted to use the models that they had in order to develop more optimal feedback strategies. And so we really wanted to build a state representation, a predictive model. And originally we're planning to do it in terms of Langevin equations based on their free energy terms and how those depended on the order parameters. But as we started getting into that process and looking at developing these stochastic Langevin equations for the order parameter space, we realized that they were developing Markov state models as the input to develop their Langevin equations. So for the dynamic programming calculation, we didn't want the Langevin equation, we wanted the Markov state model that they had already developed. So we were going to take their Langevin equation and create a Markov state model, but actually they had already done that before getting the Langevin equation. Okay. So what is this Markov state model? Okay. So it's just a collection of probability transition matrices between discrete configurations. So there are a lot of different terms for this, but Markov state model is the term that we will use. But the main idea is that we develop these equivalence classes in terms of our order parameter space. Here we have local crystallinity and global crystallinity. So we really just discretize the space. So within each box, we say, well, these configurations, if they're all in the same box, they're all about the same, and they're all going to evolve about the same in the future. So then we can collect data either from simulation or from experiment to see under a particular either low voltage, blue, or high voltage, red, where does the system go if it starts in one configuration over a fixed time interval? So basically, we discretize everything, okay? So we discretize our state space, we discretize our time, and we discretize our action space. Everything is fully discretized. And then we collect samples, and we learn, so this is the machine learning step, or empirical modeling step. We learn these transition matrices from data. And this provides a predictive model that is not restricted to a particular underlying physical representation of the system. And so it's kind of a local modeling approach based on collecting a lot of data. And we then construct a transition matrix from each state I to each state j under each action. Okay? So we just collect a lot of data, make histograms, and use that to approximate probabilities. So this is relatively straightforward, although in practice it can be kind of tricky. Mostly you just need enough data. So there's a paper here that's also cited in the manuscript that we have on best practices and suggestions for constructing this Markov state model. And here's a schematic of how we would go about doing that. So we start off and we have a configuration here. We have all of our particle locations. And then we take some samples from that in our order parameter space. So when you do this, you might collect some samples under low voltage and other samples under high voltage and access different regions of the state space. Of course, you can also switch between the levels and really enrich the samples that you're collecting. But first you collect some initial samples to access certain regions of the state space. You're probably, some regions probably you're not even going to be able to access, and others you just might not happen to access. But you take these samples and then you do clustering of some sort to develop these discrete states. Could be a grid-based approach or a clustering approach. But in general, each of these discrete states is not going to have been sampled under each input. But in order to decide on the optimal action, we really need to have information about where the system goes from each state under each action. Otherwise, how can we choose the best action, right? So there's really an important resampling approach here where we go in each box, we take multiple samples under each input. Now this is where having a detailed simulator like the Brownian dynamics simulation is very helpful. You can do this experimentally, but it's much more difficult to initialize the system within each box. So it was helpful in the colloidal assembly case to have this very detailed many-body simulator that was pretty accurate. So once we've sampled each state under each action, we can then construct our Markov state model just by observing where the system goes under each input from each state over the time step delta t. And without Markov state model, we can then use the Markov decision process formulation using dynamic programming to construct our optimal feedback policy just as a lookup table. So then each time we take a measurement, we see where we are, and if it's blue, then we apply the high voltage. If it's red, we apply the low voltage, or however many actions we have. So that's the idea. So here are some equations, in case you've been waiting for equations. So we use really the very standard formulation of dynamic programming of optimal control. So we have our cost function J, we have the expectation over stage-wise cost and a terminal cost, and then we define the optimal policy as the policy that minimizes the expected cost. So this is all very standard, and we use Bellman's principle in order to then calculate the optimal policy. And so we really put this idea out in the literature around 2014, and then I'm going to talk more recently about our experimental implementation of this policy. So here it is. Okay, so after building our Markov state model, we then defined an objective to maximize the stage-wise reward. So here I'm going to show the infinite horizon version. And the idea is that we want to maximize global order. We're not going to worry about local order because it's actually impossible to have global order without local order. Okay, so, but we could also add that in, it wouldn't change the policy. Okay, so we just want to simply maximize global order at all times. We have a discount factor of 0.99, which over the number of steps we take actually provides very little discounting. So really, we're just saying that we want to maximize the global order immediately and to stay there. So that, and that's up in this corner really. Okay, so this is our global order here. So we want to be along this line, but really it's not possible to access this kind of lower triangle because we have to first have local order before we can have global order. So what is this policy telling us? So blue is the high voltage, okay? So this policy is really telling us that we want to push very hard on the system until we get to pretty high values of local order, because we want to rapidly assemble. But if we get to this situation up here where we have high local order but low global order, that's a grain boundary. Okay? So this is not surprising, okay, that this is our policy. I think the real power is now we can calculate when to switch, okay? When to implement this switch based on our measurement of the global order through our video image processing under the microscope. Okay? And, but we don't want to relax too much. So, if we're way over here, we have a really persistent grain boundary like that one down the middle. Then we want to really relax the system a lot. But if we're kind of over here and our grain boundary's more on the edge, then we don't want to completely disassemble. Then that would be detrimental to our objective of rapidly assembling to the ordered crystalline state. So then we want to apply a more moderate relaxation over the next time step. So we're able to calculate what are these optimal actions, where I think this objective function, this reward, really does reflect pretty well what we'd like to do. And so we can take some different interpretations of this policy. We can look at free energy landscapes of the system under our 4 different actions, our 4 voltages, that we'll consider where at the high voltage, our minimum energy is over in this corner with high global order, and then we can think about switching between these free energy landscapes as we switch between our voltage levels. We can also look at the actual experimental configurations associated with different points in this order parameter space. So under configurations 4, 5, and 6, we should just push really hard. Okay? So even though they look pretty condensed, and they're still sufficiently kind of disordered and not fully assembled such that we should still push really hard. Okay. It's only when we get configuration like 3 with this persistent grain boundary or even a grain boundary on the edge that we should take an action to relax, to allow the defect to heal out of the system so that we can ultimately get to this desired structure, and then of course we just keep the voltage high to make sure it doesn't go anywhere. So first we applied this optimal feedback policy in our Brownian dynamics simulation. Of course, if it doesn't work there, then it's not going to work in the experiment. So we tested it out in our simulation, and if we just pushed really hard on the system with no feedback, we got defects 62% of the time. This is for a final time of 1,000 seconds, and we execute switches every 100 seconds. So we're really making 10 switches during that 1,000-second time period. And so we were able to get up to 93% assembly from 62% using our optimal model-based feedback policy. And here we can follow our global order versus time, and we can see that the green trajectories, which form a grain boundary, they're the ones that then require some intervention. The blue ones never form a grain boundary, and so then they can just rapidly assemble, and the optimal policy is just to push hard. Okay, so that's how it worked in simulation, then we did it in the experiment. And actually, this time we got 100 out of 100. So I guess that's good. But there's some disagreement, right, with our Brownian dynamic simulation. I think that's okay, because we have feedback to account for some modeling error. One thing that we found in observing these particular results is that the Brownian dynamic simulator was very accurate for the assembly process, not as accurate for the disassembly. It wasn't constructed for that purpose. It still had kind of the expected physics in it, but not as well validated for that case. And so we did have some modeling error associated with that. We probably also have some effect of our not having a full state representation. We just have these 2 aggregate states. But overall, it really worked quite well, and qualitatively certainly worked the way it did in the Brownian dynamic simulation. So if we observe some particular cases here, we can watch 10 different trials of the system under the optimal feedback control. The voltage action is shown in the green at the bottom. The global order is the red in the middle. That's the one to really keep an eye on. And then the blue one is the local order. So what we can see is that over each trial, we push hard on the system initially from the fluid state, and we always get to high local order in our first time step, but in some cases, the global order is not so high, okay? So that's the case where we need intervention. So this system is stochastic, each trial is different, and in this case, only 2 of the trials, 10 trials, required this intervention. But what we could see in case 2 is that we would relax to a lower level, and then try again. Okay, well now we got higher, but still kind of plateaued out. Relax one more time at kind of an intermediate level, a 0.3. Finally, boom, we got it on the 3rd try. But you wouldn't want to do this every time. So these toggling strategies have been suggested for open loop colloidal assembly, particularly by Eric First's group at Delaware. And they can be effective, but it's really not efficient if you don't need it. Right? So here we implement this sort of toggling approach to partially relax the crystal only when needed. So we needed it again, but just one intervention here in trial 8. Okay, so now we're going to watch movie version. So you can pick which one you want to focus on here. But we have the free energy landscape that we're switching between. Here's our policy map, where we'll start out down here, and we'll try to get up here. And then finally, here's the actual movie with image processing used to show the value of C6 of the local order. So the blue ones are the ones that have local order. So you can go ahead and show the movie now. So we push hard. Now we have some grain boundaries. And so at the end of our time step, now we're going to relax and wait until the next sample, and then we're going to try again. So each time after it does relax, it goes back down into the blue region. Our time step is long enough that generally really happens at every time step. We move pretty far, and boom, now we got to the desired state. Okay, so this was a study in colloidal crystallization, but there are many opportunities also for feedback control in small molecule crystallization, which this community may be more familiar with. And what I'd like to show you here is really just briefly go through how this same approach played out in a molecular crystallization process, in particular a salt crystallization process that we work on at Georgia Tech. With application to environmental cleanup, nuclear waste separation. So the particular application is for the Hanford site in Washington State, which has many million gallons of radioactive liquid waste stored in aging tanks from the Cold War era and even World War II. And so the goal is to monitor these processes and potentially also to crystallize out non-radioactive salts. And that motivates our lab work in looking at these nuclear waste simulants. So we don't actually do radioactive experiments in our lab, but we're looking at the crystallization of sodium nitrate and sodium sulfate in water to create these duraphskyte crystals. And we have our crystallization control system here, Mettler-Toledo OptiMax, and we have it instrumented with focused beam reflectance measurement, FTIR for solution phase monitoring, as well as temperature. And that's all collected in a data acquisition and control program. So I just wanted to show you here how the same approach could be applied, but needed to be tailored for a different application and different hardware. So in this case, we don't have the same kind of order parameters like we did for the colloidal crystallization. We really need to focus on real-time measurements that we have that are robust and sensitive to material structure that we can also use to characterize the aggregate state of the system. In this case, we use the total crystal mass that we could extract from the IR measurement together with the mass balance for this batch process. And we use the total number of chord counts from our FBRM. So the total number of chord counts can be used to represent the concentration of crystals, although direct mapping isn't completely obvious. And I think this is a reason why this approach that we have developed based on measured data can be very powerful in quickly getting to experimental implementation. If we needed to create a sensor model and an estimator, that we might spend all of our time doing that. By really focusing on modeling of measurements, we can really circumvent that process and relegate it to offline calibration. So we built an empirical model based on measured values of total mass and total chord count. And here we did it directly from data. Okay? So with the Brownian dynamic simulation, we used the simulation to generate the data for our Markov state model. Here we're building the empirical model directly from our measured data. And we do have a lot of data from these real-time measurements. In fact, it's become a challenge in the pharmaceutical industry to figure out how to use all this data coming from the sensors that doesn't always have a direct and quantitative interpretation. So we've really been trying to use it quantitatively here. But we did build an empirical model. Here it was a deterministic model. We didn't build the full stochastic model, but in any case, we have a predictive model in which x, the next time step, is a function of x at the old time step, and the input. Here the input is actually the supersaturation to the system. Our actual input is really the heat going to the water, to the temperature that finally drives the supersaturation. But because we had a good model relating temperature and supersaturation, we used supersaturation as our input here, which simplified the modeling somewhat, as well as the physical interpretation. And also we formulated a finite time dynamic programming problem here. We wanted to achieve a target in our mass count space at a final time. And so as a result, we have a time-varying policy. So that's another difference from the colloidal assembly system. Here we have a time-varying policy. We start with the uncrystallized case in the lower left, and then we need the orange and yellow positive supersaturation to drive crystallization toward our target, but then the blue represents that we need to dissolve because we overshot our target. It's basically what the colors represent. But they change over time as we get close to our final time. Sometimes the best thing to do is to do nothing. So that's the white region as we get closer to the final time. But initially, we really don't see any white region here. Okay, so here, these are experimental results shown of a linear cooling profile over kind of the same amount of time, and how that would drive us over here to the upper right, relatively small number of crystals. We'd really like to have large crystals that we can wash more effectively, and so we want to have large crystals, so fewer chord counts, but still high mass. Okay, so our target is over here. And using our optimal policy online, we see that, again, we do have kind of some temperature switches. We dissolve sometimes in this particular experiment, but overall we're able to kind of ratchet back and forth and kind of parallel park our car over to this desired spot here that we couldn't directly drive toward. So here there's a movie version. Also, in this case, the policy is also going to be changing. And you can go ahead and play the movie. Back. We're going to start in the lower left, no crystals, and then we're going to nucleate. So we're going to have relatively low mass and high chord count, but we didn't really overshoot too much. So we're still driving with orange supersaturation there, but we do go past our target a little bit, and then are able to come back and hit the target. One thing that we realized in formulating the cost function was originally we just said we wanted to get to our final target at the final time, and then we did, but we just flew right by it. So then we realized, okay, that's not quite what we want. We want to land there nicely, right? So we had to give kind of an inverse discounting, actually, so that we would approach the target and then kind of stay there. So we needed to tailor that a little bit, so we didn't just have a flyby, so that we could park on that spot. Okay, so as I conclude the talk, I want to just go through again these 3 steps in the methodology and just kind of summarize how they played out in these 2 different applications in crystallization control. The first step was to select the aggregate variables. So in the colloidal crystallization, we used physically based order parameters. What I didn't tell you is that first we tried a different set of order parameters, and then we tried a different set, and then a different set, and we spent really a lot of time trying different physically based order parameters until we found these 2 that actually worked very nicely. So that's why I say this is really a very difficult part of the process. We also tried automated approaches for dimension reduction, including diffusion maps and other approaches, but it wasn't really clear what our objective was in terms of parameterizing that set. Did we want high variance? Not necessarily. So I think there's a lot of potential here to automate this selection, but that's not something we did for the colloidal crystallization case. But because we had full state feedback, we could choose anything. We still just didn't know what to choose. But this set that was motivated based on domain expertise did ultimately work quite well. In the salt crystallization case, we were much more limited because we didn't have full state feedback, and so we went with some quantities that we knew were important, that we could measure reliably, and that we could calibrate offline with properties that we cared about. But in both cases, we have 2 dimensions here. Of course, in a much higher dimension, dynamic programming is going to be much more computationally intensive. So you might need something like adaptive dynamic programming, proximate dynamic programming, or model predictive control might be better in some cases, or other approaches. But in this case, we were able to have 2 state variables, and dynamic programming worked very well. The second step was to learn the dynamics. And in the colloidal crystallization case, we built these transition probability matrices to create a Markov state model, and we used our Brownian dynamic simulation to do that, which meant we needed a lot less experimental data to build our model. We were able to arbitrarily initialize the system, things like that. In the salt crystallization case, we learned the dynamics directly from experimental data. We did not use a population balance model for this crystallization process, although we could have built a model like that and used it to generate our empirical model. But we built a deterministic model because we really didn't see a lot of stochastic behavior in this more macroscopic kind of case with the salt crystallization. Plus, we had less data. So we built basically probability matrices that had zeros and ones in them. Then to calculate the control policy, we really used state feedback policy using dynamic programming in both cases. There were some differences. We used infinite horizon policy for colloidal crystallization with policy iteration, salt crystallization. We had a finite time, and then we just worked backward in terms of computing our policy. But there's really nothing fancy about this step, is really what I wanted to say. So the challenge here was in figuring out how to model the system and deal with our measurements, and not actually, we really didn't have any advance in terms of the control policy calculation. So with that, I'd like to conclude. I hope I've been able to convince you today that optimal model-based feedback control is feasible at the nano and micro scales for molecular phenomenon. Because these systems are stochastic, there's a huge opportunity in improving processing efficiency and materials performance by using feedback control, and that it is possible to do it. There's still more to do. So we were able to show how this would play out in kind of the simplest colloidal assembly system, a batch system of 300 particles, but certainly if you're looking at high throughput nano manufacturing, you probably want to have a continuous process, and you might have more complicated system and more actuators, and there's plenty more to do. A major challenge, I think, is in the selection of the reduced order state for the system, and to automate that, which we have not done. And also other challenges such as robustness of the policy to modeling error. For any model-based control strategy, that's important. I also think that on the horizon going forward, there's continue to be advances in technology that will be very helpful, especially for sensors, for feedback. Real-time imaging is continuing to develop. So for the colloidal assembly case, we just used an optical microscope, nothing fancy about that, but you could also image in 3D with confocal microscopy if we wanted to control a 3D crystal, and that's something that the Bevan group already has the capability to do. But also, in situ TEM is continuing to advance, where we can actually watch, there are movies where you can watch the atoms move around in real time and see how they assemble. So I think that's very exciting going forward, that we could really start to control actually at the atomic scale and have full state feedback. I'll also point out that the optical video microscopy and image processing with full state feedback that we had for the colloidal assembly process is probably not what you want to do for manufacturing. That's probably not going to be practical. But it was really helpful for us to understand kind of how much information we really needed for feedback. And it turned out we really just needed a couple of order parameters, global and local order. And those, possibly could be measured with simpler sensors, non-invasive sensors. We also were able to see in the cell crystallization that we could really do a lot also with the quantities that we could measure in real time from our process analytical technologies. So with that, I'd like to thank my very important collaborators in this work, Professor Michael Bevan, who's did all of the experiments and also really developed the hardware and framework for feedback control in colloidal crystallization. He's in the Department of Chemical and Biomolecular Engineering at Johns Hopkins University. Also, my close collaborators in small molecule crystallization at Georgia Tech, Ronald Rousseau and also Yoshi Kawajiri. And funding from the National Science Foundation, as well as the Department of Energy, through the Consortium for Risk Evaluation and Stakeholder Participation and the Nuclear Energy University Program. I really want to point out the researchers who were very important in this research, who did the actual work. Dr. Yu Jianju was a postdoc who really formulated the idea for the colloidal crystallization as a Markov decision process and led our early preliminary work on that project. Xuan Tong is a PhD student whose thesis really was on developing and implementing colloidal crystallization, including the experimental implementation. And Dan Griffin, who worked on the cell crystallization, and all of them have moved on to the next stages in their lives, but they were, this is really their work that I'm showing here today. And also like to thank my current research group, who is carrying on this work. And here are 3 publications if you're interested in reading more and learning more. The first 2 are the papers that describe the first experimental implementation in each of the 2 case studies. And then also we wrote a conference paper for this conference, really summarizing the work in this area. So if you're interested in that, you could check out the conference paper for this conference. So thank you very much, and I'd be happy to take any questions.
Marta, thank you very much. That's a great talk, very clear slides. I want to open the floor for questions. We do have a few minutes for questions. If you can identify yourself.
Hello, good morning. I'm Francesco Corona. I'm from Brazil. Thank you for the very nice talk. It was exciting to listen to your journey through this modeling this system. I have a question, but I guess I can sort of formulate as a threefold question because I have actually many questions. I was wondering if you could articulate a bit more about how you estimated the transitions, the probability transition metrics using the simulator. And I would also like to ask you, was it really needed to discretize the parameters? I mean, the parameters and not work with actual continuous random variables and see how they would actually evolve in time. And okay, well, last question is still related to the other parameter, which I guess is also your biggest concern. I believe that they are Markovian in a sense, but if I'm understanding, they are expected values. Basically, you average over all the particles and you count how many nearest neighbors they have locally and globally, right? Wouldn't it be perhaps kind of more complete description of the system if you would consider the full distribution of, for example, nearest neighbor distances rather than a binary, or actually quantified numbers of nearest neighbors, their actual distances?
Yes, thank you for those questions. The last question, we have looked at histograms or of distributions of order parameters. So I think there is a lot of information in terms of, say, the distribution of C6 over various particles. That certainly, if we wanted to identify a grain boundary conclusively, we could get more information by looking at the C6 histogram as opposed to just looking at the average C6, absolutely. So I think in this case, we were looking for a two-dimensional representation of the system. Okay, so, and maybe we could have gotten that two-dimensional representation from the histogram of C6, and we didn't need the Psi6, for example. But in terms of implementing the dynamic programming, kind of understanding the policy, evaluating and validating the results, and troubleshooting, it was very nice to have two dimensions. So for these two order parameters, we never found a case where we looked at two configurations and said, okay, these are very different but mapped to the same point in our order parameter space. In previous iterations, I had the loop with the 6 blocks where we went through building the model. There was a feedback loop there of controller validation, and we went around that many times. Okay? And we would find configurations. We would go into troubleshoot, try to figure out what's going on. We would find two configurations were clearly very different, but had the same point in order parameter space. So, but absolutely, there's a lot more information in the histograms of C6, not just in the average.
And the actual distances between nearest neighbors,
yes,
not just counting.
Yes. So when we first kind of implemented this type of approach in Monte Carlo simulation over a decade ago, we looked at radial distribution functions, and we did principal component analysis on the radial distribution function. Now, that's also missing some angle information. It's just distances. Okay. So I think you're spot on. There's a lot of information in terms of relative distances and angles and configurations. And then the question is, how many of them do we really need, given that we have feedback to robust by against uncertainty and incomplete information. So then questions about the Markov state model. Do we need to discretize? No, we do not need to discretize. But we, at some point, decided to go with the Markov decision process framework. And so then having a discrete Markov state model was the input for that. But certainly you could have a continuous representation. And we've looked at local approaches for Gaussian process modeling over the years to do local modeling in continuous space. In this case, we started going down the Markov decision process pathway. Actually, the discretization was not so central in the salt crystallization. So there are a lot more details in that paper about explicit MPC and continuous modeling and all that. So actually, it's not really not important. What's important is that you have a predictive model. And there are good reasons to not want to do the discretization, because then you discretize very finely because you want to be very accurate or sufficiently accurate. Then you need so many samples. Okay, so you're asking about sampling. We just sample and then approximate a probability with a normalized histogram.
The transition probability metric is stationary. You won't change over time.
No, it does not change over time, but for each action. Okay, so we constructed it separately for each of our 4 actions. Okay. We constructed 4 different probability matrices, but they do not change over time. I mean, I think it's a very viable approach, having tried a lot of approaches, to just discretize everything. But it's not the only approach. You don't have to do that. You don't have to do that. In fact, we were originally planning to use these continuous Langevin equations until we realized, we could just take those Markov state matrices you've already built and plug it right into MDP, and we've got it. Yeah. But then we didn't have the right state representation, of course.
Okay. Thank you.
Thank you for those questions.
Another quick question.
Thank you. I'm Eduardo Campo Nogara from Florianópolis. So thank you for coming all the way down from Georgia to Florianópolis. Well, the first colleague asked all the questions, but I was particularly interested in the continuous state and action space. I mean, so you gave a partial answer to that. So what I'm really interested is whether there would be benefits regarding to the final product of considering continuous state and action spaces, and what would be the difficulties to that? Because one could consider using function approximations, generalizations, and maybe even neurodynamic programming. So that would be my question.
Yes, I agree with all that. In this particular case, I felt like the policies that we got, for example, in the colloidal assembly, did very much make sense in terms of the type of action that we would take, but exactly where are the boundaries? Those boundaries of where we switch might change if we had continuous variables. So probably we could do better with either finer discretization, more actions, or fully continuous variables and distributions. I think those are just details. I think the key points are that we need to select aggregate variables, our first step. Then we need to learn a model for the system, our second step, and then we compute our optimal policy as the third step. I think the rest is really just details. But it is difficult to build these models, I'll say. And so, I think that when considering kind of the practicalities of building the model, then one can determine if a continuous approach is viable, or if what can be done given the hardware constraints and computational constraints and all of those things. But certainly, our discretization was just the details of the implementation, really not central to the methodology. So continuous variables, could certainly do better than discretizing. Yes.